Okay, so an entirely new topic here, new chapter. This is the final chapter and probably the most important one. It's certainly the most useful one going forward, especially if you're taking Physics 2, electromagnetism. You're going to be talking about vector fields quite often. So vector fields. What is a vector field? So maybe before we answer that question, let's remind you what a scalar field is. We have talked about those extensively, right? A scalar field is essentially a function of your position, right? Or a scalar function, right? So some function that depends on, say, x and y if you're in the xy plane, or x, y, and z if you're in space, right? So yeah, we've seen these many, many times. Here's an example. Suppose we have a function of x, y, and z. That's just x squared plus, let's make it interesting, y cubed plus z to the fourth, right? So this is a scalar field, right? Every point in space has a different value, right? So the value that corresponds to the point 2, 3, 1 is going to be, well, 2 squared plus 3 cubed plus 1 to the fourth. So 27, 28, 32. So at the point 2, 3, 1, we associate that with this number 32. Right? So that might be, I don't know, the temperature at that point, right? So a good example of a scalar field is the temperature. If I can spell it, temperature. Right? So, yep, every point in space has a different temperature. If you move the thermometer around your living room, the temperature is probably not going to change all that much. It'll probably be about the same, right? But if you move your thermometer, 200 miles south of here or 300 miles north of here, you can expect the temperature to change significantly, right? So yeah, temperature will depend on where you are, right? So it's a good example of a scalar field. So what is a vector field? Well, as you can imagine, it's still a function of position, but it's now a vector function of position. So instead of a little f here, we're going to use a capital F, and we're going to put an arrow over it because it is a vector. It could be a vector in the plane, right, in the xy plane, or it could be a vector in space that depends on both xy and z, right? So yeah, so these are vectors, right? So now every point will not just have a number with it, it'll have a number and a direction. It'll have an arrow, right? So let's just stick with the xy plane for now, because it's hard to draw in space, right? So at this point here, you might have this vector. At this point here, you might have, I don't know, this vector. At this point, you might have a very small vector. At this point, you might have a very long vector, right? So every point in space will have a different vector, right? And, this is almost not a continuous one because as you vary from here to here, your vectors get very different. So our functions will generally be continuous. So these will be continuous vector fields for the most part, where the arrows, flow continuously. Right? You're suddenly not going to change from this vector to right next door to this vector here, right? So that's the idea, right? Every point in space has a different vector, right? So, maybe a familiar example. Obviously, temperature does not have a direction with it. Temperature is just a number. And if you want to measure the speed of the wind, right? If it's a windy day, you go outside, you can, there are devices that measure the speed of the wind. And yeah, so that's also a number, speed. But if you want to measure the direction the wind is traveling in, like let's say the wind is basically traveling this way, right? And over here, it might be a gust of wind. It might be a little bit faster in various directions. Then that's a vector field, right? So wind velocity is a good example, a somewhat familiar example of a vector field, because the wind is not just traveling at a certain speed, the wind is traveling in a specific direction, right? And if you can imagine a vector field that looks like this, maybe not the best picture, but if it's going around, that might be a tornado or a hurricane, right? So something, well, here, let me do it this way, right? So you can have a circulating vector field like this, indicating that the wind is just going around and around and around, you know, as in a tornado or a hurricane or typhoon or like that, right? So yeah, wind velocity is a good, familiar, intuitive example of a vector field, right? And of course, when you get to your physics courses, especially the second semester of physics, you will talk about the electric field and the magnetic field. And these are further examples of vector fields. You know, they're ones, well, depending on what you're doing in life, may or may not be familiar to you. But once you take your physics course, your second semester physics course, you will be more familiar with electric and magnetic fields. You know, I mean, like wind, it's not something you can see, right? But you can, you know, you can experience the effects of the electric and magnetic field, right? And I guess that's not too different from wind velocity. You can't see the wind, but if you see, say, a dust cloud and dust particles are kind of flying along here, then that gives you some idea of what the wind is doing. So you can't see the wind itself, but you can see the effects of the wind. If, you know, if leaves are blowing on a tree, you can see the effect of wind. So yeah, same thing. You cannot see the electric or magnetic fields; they're invisible. But you can, you know, experience the effects if you have electric charges or moving electric charges in the case of magnetic fields, right? Or just, you know, just for a magnetic field, just take a ordinary magnet. We call it a ferromagnet, which is a permanent magnet. Those are R's. I'm sorry, can't spell. So ferromagnetism is the most familiar magnetism that you get with those, you know, magnets you put on refrigerators, right? So those are the permanent magnets, you know, typically made of iron, and you can certainly feel the effects of that when you put it near metal, right? In any case, that's for a physics course, right? So we will talk a little bit about electric and magnetic fields later. Oh, and of course, the gravitational field is a vector field. And this is one that we can't see, but we can certainly, in everyday lives, we experience it, right? Here's the floor. If you drop something, it's going to go down because of gravity, right? So this is the gravitational field, right, near the surface of the Earth, which is where we are, right? The Earth is pulling things downward, right? And it is, you know, it's roughly a constant gravitational field, the same acceleration pretty much everywhere we are. You know, you'd have to go pretty far around the Earth to experience a different gravitational field, right? So, you know, because the ground is roughly parallel where we are, but over the course of the Earth, of course, it pulls inward, right? So I'm just taking a tiny piece of the Earth here, and over that very tiny piece, it looks flat, you know, locally, and that's why the gravitational field is roughly constant over, you know, a small location. Right. But in general, it points radially inward. You know, just like the electric field does. For negative charge. For positive charge, it points outward. Okay, enough of that. Let's get to some examples of vector fields in general. whether they're electric, magnetic, gravitational, or wind velocity. We're just going to talk about generic vector fields, so in general. Okay, so we have some generic vector field f in the xy plane. So at a particular point, say at this x and this y, you have a vector, right, represented by capital F with an arrow over it, right? Again, the book doesn't have the arrow. It just puts an F in bold type. But I'm going to use the arrow notation if that's okay. Right, same thing. Right. And what do we know about vectors? Well, they have a magnitude and direction, but they also have components. They have the x component and the y component, right? So, you know, various books have different notations. Our book settles on m and n for the two components, right? So we're going to use m for the x component, and because it varies with position, right, a different x and y will give you a slightly different vector, or maybe a very different vector. So these m and n's, of course, are functions of x and y in general. So that's the x component, and then the y component will be n. Right? Or, again, if you prefer, you can use the usual bracket notation. Right, and now we've discussed this several times. You can actually use a row vector, a column vector, but we're not going to do that, right? This book doesn't do it. This is more for a linear algebra type situation, so I wouldn't worry about that here. But we know that these two notations, the linear combination of I and j, or just the bracket notation, right? Of course, now we can also have a vector field in space. Right? So at every point in space, so now we add the z-axis, so now these are points in space, and they have a vector pointing in some direction in space, so now you have three components. The x component will still be m, the y component will still be n, and what comes after n? Well, O, but that's a horrible letter to use because it looks a lot like a 0. So we just go to the next letter, P. So P will be the z component of that vector at that point, right? So yeah, so here it looks like the x component will be negative. Well, the y component might be positive, but the z component might be positive as well. So again, this is, you know, the usual notation here, or the usual representation in terms of x, y, and z, right? Although I know we usually put the z-axis vertical, and then this is the y-axis, this is the x-axis, but it's still a right-handed system, so it doesn't matter. Again, a lot of physics books like to use the z-axis coming out of the board, but in our usual way to represent space, we do the z-axis vertical. Okay, so yep, so these are vector fields in general, and you know, this might seem like a relatively new concept, but in terms of what they represent physically, but we have seen examples of vector fields before. And they can actually arise from a scalar field in the following way, right? So here's our first actual example. If we take a scalar function, right, which is not a vector, right? Let's say it's just x cubed minus x squared y plus y cubed. Okay, so yes, scalar function, right? You plug in a number, you get a number. Or you plug in, let's say, a set of numbers, and then you get a number. Can I do this in my head? Let's see, 8 minus 12 plus 27. So 27 minus 12 is 15. 15 plus 8 is 23. Okay. Right, so again, this is a scalar, not a vector. Right. However, if you take the gradient of this function, right, remember, it is a vector. Oops, I forgot the f here. It's the gradient, or del, of f. And remember what it is. It's a vector. It's a vector whose m component is a function of x and y, and n component is a function of x and y, are the partial derivatives, right? The partial of f with respect to x is your m, and n is the partial of f with respect to y. Right? And I know I should use a z here, but right. So in the usual notation, right, you can also do f subscript x and for the I component, and then f subscript y for the j component. Right? But those are our m's and n's for the gradient, right? So the gradient of a scalar function is a vector field. Right? Right. And so what is it for this particular example here? What is the gradient of this function up here? Again, you should be able to do that in your head by now. So your x component will be the partial with respect to x, right? So it'll be 3x squared minus 2xy. So that's your m. And then your n will be the partial with respect to y. So negative x squared plus 3y squared times j. Okay? Right? So again, this is your m, this is your n. It is a vector field. Right? And in fact, if you plug in a point for x and y, well, let's do the same point, 2 and 3. Right? You now get a vector instead of a number. Right? So let's see. 3 times 2 squared is 12. 12 minus 2 times 2 times 3. Oh, that's also 12. Oh, so that's just going to be 0. Oops. And then let's see, minus 2 squared, so minus 4 plus 3 times 3 squared is 27. So you just get 0i plus 23j. Wow. So that is just a coincidence, right? It has nothing to do with this 23 here. That is just a pure coincidence here, right? Because this is a vector, not a number, right? It has two components, the 0 and the 23. In this notation, of course, you don't have to write 0i plus 23j, but in this notation you do, because if you just write 23, that's a scalar, it's a number, right? So yeah, so maybe just a bad example, but you know, we didn't have to plug in the 2 and the 3, right? We could plug in some other point. How about negative 1 and 4? So if we do that, our m, our I component, our x component will be, let's see, 3 plus 2 times 4. 2 times 4 is 8. 8 plus 3 is 11. So 11i. I just double check that. Yeah, 8 plus 3, 11. Okay. And then for the n component, that is the y component, we get negative 1 plus 3 times 16. So 16 times 3 is 48. 48 minus 1 is 47. So, yep, we just get the vector 1147. Right. So at this point in space, you have this vector here. Got it? Yeah, and just to show you that if I take f of negative 1 and 4, you don't get either 11 or 47. Well, at least I hope not. So, gosh, I forgot what f is. It's x cubed minus x squared y. So x cubed minus x squared y plus y cubed plus, yes, plus. All right, so this is going to be negative 1 minus 4 plus 4 cubed. So 64 minus 4 is 40. 40 minus 1 is 39. Yeah, I can't do math, right? 64 minus 4 is 60. 60 minus 1 is 59. There we go. Okay. Sorry about that. Long day, right? Okay, so yeah, so basically the vector field, right, has nothing to do with the scalar that you get by plugging in the number, right? Effectively, the 59, if you remember, is the y-coordinate of the surface. So if you think of this function, z as a function of x and y, right, what you get at that point, okay, let's say this point is negative 1, 4. I know that's not accurate, but just to give you the idea, right, the z-coordinate here, right, the z-coordinate will be 59, right? So that has nothing to do with the vector field here. So what does the vector field represent? Well, remember, being the gradient, the vector, this vector 1147, that let's say points this way, will point in the direction in which the surface is increasing. It's the steepest, right? It's basically pointing in the direction of the steepest descent. So maybe not exactly accurate here, right? So I drew the wrong surface, right? If the vector is pointing this way, we're going straight up the hill. If the vector is pointing this way, that'll be the negative of the gradient. You'll be pointing straight down the hill. So the gradient points in the direction, oops, sorry about that. The gradient points in the direction of the steepest descent. So if you want to go up the hill in the steepest way possible, take the gradient, and that'll point in the direction of the steepest descent. And if you want the actual magnitude of that slope, you would take the magnitude of the gradient, which is whatever it is, right? The square root of 11 squared plus 47 squared is just some number. So that's the maximum directional derivative at that point. So yeah, we talked about that way back in chapter 13. And so here it is again, right? So just the idea that the gradient of a scalar function gives you a vector field. Okay, but let's take an even easier example. So here's a vector field, xi plus yj, or it's just a vector xy, right? And yeah, so in other words, m is just x, and n is just y. So this is a vector field in the xy plane. And the reason why we're doing this example is that we can actually draw the arrows here, draw the visual representation of some of these vectors. All right, close enough, right? So I'm just going to use 1, 2, and 3 here as the usual scale. Okay, so let's just plug in numbers. If we plug in 0 and 0, of course we just get 0. So at the origin, it's the 0 vector. So just a point there, right? But what if we plug in, say, x equals 1, y equals 0? Well, then we get the vector 1, 0. So at the point 1, 0 here, we have a vector pointing to the right 1 unit. If we plug in 2, 0, we get the vector 2, 0, which points to the right, let's see, 2 units, right? And you can see at the point 3, it points 3 units. It's even longer. And the same is true in the vertical direction, right? If you plug in 0 and 1, you get the vector 0, 1, which points upward, right? 1 unit. And if you plug in, say, 0, negative 1, you get 0, negative 1, points downward, right? And if you plug in negative 1, 0, points to the left. What if we plug in x equals 1, y equals 1, and we get the vector 1, 1. So at 1, 1, we get a vector that points this way. So I think you get the idea. Negative 1, 1, you get a vector that points this way. At 1, negative 1, you get a vector that points this way. At negative 1, negative 1, you get a vector that points this way. And so at each point, you get a vector that essentially points outward in that direction. Right, this point might be, no, it's not quite right, but you get the idea. Right. So essentially, all your vectors just point outward from the origin, right? So we can think of this as just a radial vector, a vector that points radially outward. Makes sense? Yep. So a good example of a vector field that can point outward like this. Of course, if you wanted to point inward in the opposite direction, that's an easy thing to do. Just make m negative x and make n negative y. So just take the opposite direction, and now you're pointing the opposite direction. You're pointing inward instead of outward, right, at each point. Okay. So here's another example. It's negative yi plus xj. And this is the same example in the book, but it's a good one. It's to draw out here. So at 0, 0, you just get the 0 vector again. At 1, 0, so I already wrote all this out, so we don't have to compute anything here. You get the vector pointing straight upward, right? At 0, 1, you get the vector pointing to the left. At negative 1, 0, you get the vector pointing straight down. And then 0, negative 1, you get a vector pointing to the right. And to fill this out a little bit, you get this vector here, this vector here, this vector, oh, sorry, wrong place, I think. And this, and we're just going around. These, I think, will have half the magnitude here. This will have twice the magnitude, and so on. Right. Yeah, so essentially, you're just going around. Remember I mentioned one about the circulating field? So if you take a point and just follow it, you just go around in a circle. So if this is the wind, right, the wind is just carrying you all the way around in a circle, as it typically does in a hurricane or a tornado, right? Yeah, so this is a good example of what's called a circulating vector field. Circulating or rotational. I think the book also uses the word solenoidal. A solenoid is just essentially like a cylinder, but you might have like a coil of wire going around it. So this is a good example that produces sort of a straight magnetic field inside. But yeah, so I don't think I'll use the word solenoidal. Circulating rotational is good enough, right? So yep, you're just going around in circles. In this case, counterclockwise. If you want to go clockwise, yep, just change the signs, right? Make it a plus y and a minus x, and then you'll go around clockwise instead of counterclockwise. So yeah, I hope that helps. Again, a better picture in the book than the one I drew here, but it's the idea of a circulating magnetic field, right? So the radial magnetic field is typically what you get for an electric charge, right? So this is an electric field of a point charge at the origin, let's say. So this would be like a proton, a positive charge at the origin. And here you have to imagine the z-axis coming out at you. This is going to be an electric current on the z-axis. This is an electric current on the, let's see, positive z-axis, which produces a magnetic field, right? So this is an example of a magnetic field. Okay. Anyways, yep, two good examples, and we'll see several others pretty soon. So here's two more examples. I'm just calling them example A and example B. The one in blue on the left here, I'm using F for the vector field, and the one on the right, I'm calling it G, because they are two different vector fields. I don't want to get them mixed up by using the same letter, right? So yeah, we did use G and F for two different vector fields already. Right, so these are two examples of vector fields, right? Every point will give you a different vector, right? And the point here is not to graph it. We're not going to try to draw the arrows here. It's going to be way too complicated. But the point is, right, you could do this. You could have, vectors pointing in some directions and others. So a little bit harder to visualize what the arrows are here, right? We're not going to try to graph it. Of course, you can use software to do that. You can plug it in and it'll draw the vector field for you if you want, right? So here's the question I want to ask about these two vector fields, right? And this has to do with something that I kind of mentioned back in chapter 14, right? The question here is the following. Is this vector field equal to the gradient of some scalar function little f? Right? That's the question, right? Because, just a few minutes ago we talked about if I take a scalar function, little f, I can always form a vector field by taking the gradient, right? I can do that, and I get a vector field. But this is the reverse question, right? This is taking a vector field and saying, well, can I write it as the gradient? Can I write it as the gradient of some scalar function? And if so, what is that scalar function, right? What is the little f here? So, right, so can I write the vector field f as the gradient of f? And if so, right, can I find that function f? Okay. So yeah, this is something that you actually did for homework probably in, I don't know, some number of sections ago, somewhere in chapter 14. I think there might have been an exercise about this. But let's go through it again just in case, right? That in order for this capital F to be the gradient, what do we know about the gradient? It's going to be a vector field whose components are the two partial derivatives. The I component is the partial with respect to x, and the j component is the partial with respect to y, right? So we get two equations here, right? We equate the I component of these, and let's just write that down, that the partial of f with respect to x is just 2xy cubed, okay? Likewise, we have this component, the j component, that has to equal the 3x squared y squared, right? So the y partial of f is 3x squared y squared. So can we find f, the scalar function? Well, sure, we just have to integrate, right, the 2xy cubed. This time with respect to x, right, because this was the x partial. So it's the integral in terms of x, right, dx. And, boy, I'm running out of space here, but let me try to squeeze it in. Sure, with respect to x, this is just x squared times y cubed. Remember, though, not just a constant here, but any function of y, right? If I add, sine of y here, well, if I take the derivative with respect to y, I get cosine y. But remember, I'm taking the derivative with respect to x. And the derivative of sine y with respect to x is 0 because we're treating y as a constant. So we're going to have to use, I'm running out of letters here. How about little h of y, right? And now we do the same thing with the y partial. We have to integrate that if we want to get our little f. But now we're integrating with respect to y. And if we do that, the 3x squared is just a constant, right? And when we integrate y squared, we get y cubed divided by 3. That cancels. And now, of course, you're adding any function of x, right? So I think we have our answer here. Our little f, our scalar function, is really just x squared y cubed, plus, well, what function of x is also a function of y? Right? Anything that contains an x in it, like, e to the x, will not be a function of y. And anything that's a function of y, like my, sine of y, won't be a function of x. So the only thing that's both a function of x and y at the same time is a number, a constant. Right? I'll call it c. Maybe I'll call it little c here. It's just some number, right? And now we can check that this is correct. If we take the x partial, we get 2xy cubed, which is what we had, yeah. And if we take the y partial of x squared y cubed, we get 3x squared y squared, which is, yep, what we had. So the answer here is yes. We can write this vector field as the gradient of some scalar function f. And what is this little f? Well, it's right here. Okay. So because this little scalar function f here, right, remember this is a scalar function, not a vector. When you take the gradient of this, you get a vector field. But the little function, the little f itself, is a scalar function. And in fact, we're going to give it a name, right? We're going to call it the potential function. And for those of you who've had physics, you probably know why, right? We think of this as sort of like the potential energy, right? Which is not a vector, right? It's a scalar. Potential is a scalar, right? Okay, so yeah, we're going to call this the potential function here. So, right, so that answers the question. Is the vector field f a gradient? Is it the gradient of some function? And the answer here is absolutely. And in fact, we can find, by just doing the integrals here, we can find our little f. We can find our potential function. Okay. Now, let's do the same thing with g and see if we can answer the same question, right? So I'm going to move this a little bit this way here. Oh, I need to, shoot, sorry, give me 1 second. I needed to move it a little bit to the right here, just to create a little more space. Okay. Yeah, so again, the question is, right, is G, the vector field, capital G, is this equal to the gradient of some scalar field, little g? And if so, can we find the little g of xy? Can we find the potential function? Okay. So we do the same thing, right? We are assuming here that capital G, the vector field, is going to be the gradient of, well, yeah, let's write it as the gradient of little g. And that just means the partial of g with respect to x times I plus the partial of g with respect to y times j. So we're just equating the x and y, or I and j components, right? So if the partial of g with respect to x is equal to x squared, right, then when you integrate x squared with respect to x, right, you get 1/3 x cubed plus some function. Can I use h again because I'm running out of letters here? h1 of y. Any function of y, if we take the partial with respect to x of h1 of y, we just get 0, right? So yeah. So far our g of x looks like it's got to be 1/3 x cubed plus a function of y and only y, right? Because obviously if we have an x in here, we won't get, the derivative won't be just x squared anymore, right? All right, now let's do the same thing with the, sorry, that's g, with the y partial derivative. The y partial derivative is x times y. So if we integrate, right, x times y, this time with respect to y, what do we get, right? Well, remember, the x is a constant, so that can come outside. And when we integrate y with respect to y, we get 1/2 y squared, right? So 1/2 xy squared plus some function that only depends on x, right? So yeah, we get 1/2 xy squared plus some function that can only depend on x. We'll call it h2 of x, right? So there it is, right? We have our potential function, right? We have our function. It's 1/3 x cubed plus some function that's only y. And it has to be 1/2 xy squared plus some function that's only a function of x. So can we do this, right? Well, this function that's only a function of x, here is a wonderful candidate for that, right? 1/3 x cubed only depends on x. So h2 of x, I think we can just let that equal 1/3 x cubed, right? Plus a constant. We'll get to the constant later, right? And then we also have to equate h1 of y with a function that only depends on y. So what could that be? Well, I suppose that could be this. Unfortunately, it can't because there's an x here. Remember, this can only be a function of y, not x. So that's a problem, right? So this h1 of y here, the only thing that it could be is the other term here, the 1/2 xy squared. But it's not just not just a function of y, right? If it was just 1/2 y squared, that would be okay. But remember, the x is certainly a factor of this integral here. So there's no match, right? These things don't match here. So the conclusion is that there is no potential function. There is no little g here, right? So the answer in this case is no, right? Capital G, the vector field here that I messed up, right? But x squared I plus xyj, right? This vector field cannot be written as the gradient of this little g here. We tried finding the little g, and it doesn't work, right? The h2 of x is fine, but the h1 of y is not going to be just a function of y, right? So there's no way to match the two together, right? These things would have to be equal, and they're not, right? And that didn't happen for f, right? We managed to match these two partial derivatives, right? When we integrated them, we had two scalar functions, but it was really the same for both, right? The x squared y cubed works for both. When you take the x partial of x cubed x squared y cubed, you get the 2x y cubed. And when you take the y partial of xy cubed, you get 3x squared y squared. It works for both, right? It's got to work for both. But yeah, here, again, if you're thinking, well, can't I just add them? Can't I just do 1/3 x cubed plus 1/2 x y squared, right? And then plus the c, of course. Okay. Well, again, let's try it. Let's take the two partial derivatives, right? Let's take partial of g with respect to x, or g sub x, if you will. And if we do that, we get 3 times 1/3 is 1, right, times x squared. But we get plus 1/2 y squared, right? And you can see that's not the original vector field. We only had x squared, right, as our m, right? In other words, this is not equal to m. M was only equal to x squared. We did not have this 1/2 y squared. So we can't just add it. We can't just make it that, right? Right. Now the y partial I think works, but both of them have to work, right? If we take the partial with respect to y, we get 0 plus xy, right? And then the derivative of c is 0. So yeah, the y component works just fine. The y component was xy, as it was up here. But they both have to work, right? It's a vector field consists of the two component functions, the m and the n, and they have to work, right? They have to work for both. So the problem is that the x component, the m, is not what it should be. If you think that this is the scalar function, check. Take the partial derivatives, and they should match the original vector field, which again I erased already, but here it is. Well, I didn't erase it, but it's way up there, right? It's x squared I plus xyj. And yeah, the xy works, right? That is the y partial of g. But then the x partial of g should be equal to this, and it's not, right? We have that extra 1/2 y squared. Doesn't work. Okay, So, oh, I'm sorry, I'm going way above here, right? So two different vector fields. One of them can be written as a gradient, one cannot, right? So that's the right. There's a difference between these two vector fields, right? And so we need to distinguish between the two, and we use the following word for a vector field f that has a gradient, right? We call this vector field conservative, right? And so the vector field g then, well, is not conservative. If it does not have a scalar function, it is non-conservative or not conservative. Okay? Right. Has nothing to do with their politics, right? Conservative in this case means it conserves energy. If you think about the potential function, remember I mentioned its potential energy, right? So yeah, so this vector field here would conserve energy, right? So F conserves energy. Conserves energy. That's why we call it conservative. And G, this vector field here, would not conserve energy. So this is non-conservative. Or just say not conservative, right? Either way. Right? So yeah, the vector field G would not conserve energy. And look, if you've taken physics, even physics 1, probably one of the first things they tell you in the first couple of weeks of class, they say, look, energy is conserved. Energy is constant. It doesn't change, right? And so if you're wondering, well then, how does that coincide with this vector field? If it doesn't conserve energy, then it's not realistic, right? It's not an actual vector field. It can't be an electric field or a magnetic field or a gravitational field, because gravity conserves energy. The electrostatic force conserves energy, and the magnetic field, not so much. Again, that might be getting a little more advanced than we need to talk about. But in terms of the electric and gravitational field, those are conservative vector fields, and so they always have a potential function. And in fact, in a lot of your physics course, right, part of the job is to find that potential function. Right? If you're given the vector field, here's how to find the potential function, right? Or the potential energy. And perhaps at this point I should warn you that in your physics courses, they don't do exactly the same thing. So let's say we have an electric field. First of all, they probably don't use little f for the potential function. For the electric field, you might think they use little e, but we already use little e for the electron and other things. So they'll either use the Greek letter phi, which again might be confused with the phi angle, or more likely they use just capital V. Right? Capital V could stand for voltage, which is a potential difference. Sorry, voltage or potential difference, right? So yeah, V for the potential or potential energy. But the convention is that they use a minus sign here, not a plus sign. And this is also true in terms of gravity. If you think of the force of gravity, it's just the negative of the gradient of the potential energy. So yeah, we're not going to use that convention. This is a convention, right? And we're not going to put the minus sign there. We're just going to leave it as positive, right? On the other hand, if you make a mistake and put a negative sign, I'm not going to worry about that usually. So yeah, why the negative sign? It's just nature, right? If you have a potential, let's say you have a bowl here, and you put a little marble inside the bowl, on the side of the bowl here, and you let it go, well, what's going to happen? It's going to roll down the hill, right? It's going to roll up and then back and forth, right? So if you think about this function in terms of x, right, this is just one-dimensional, so this is really just the negative partial derivative of u with respect to x. So clearly if I take the derivative is just the slope The slope of the tangent line is, well, some positive number, right? So this is just the partial of u with respect to x, and we know it's positive. But then the partial derivative is then the force. I should put an I here to make it a vector, because these are vectors, right? So which way is the force? Which way is gravity acting? Well, gravity is acting down, but which way is the marble moving? It's moving to the left, right? It's moving this way. So in the negative direction. So that's why, of course, they use a negative sign, because the force is in the opposite direction of the derivative. The derivative is positive, but the force is in the opposite direction, right? So that explains why you get a negative sign in your physics courses. Here, we're just not going to worry about that. So our force is essentially the negative of what it should be, right? Our capital F would be essentially backwards here. So not a distinction we're gonna make, simply because we're not going to talk about these physical situations very much. We're thinking about these vector fields more in the abstract, at least in this course. Okay, so yeah, the definition here, we're just going to define F. We have our vector field, and actually we can do this in any number of dimensions here. So we have mi plus nj plus p times k. These are the components of the vector field in space. So this vector field is called conservative if there is a scalar function, which I'm going to call little f, right? So no arrow here. It's not a vector. It's a scalar function, right? Which we call this the potential function for reasons I already mentioned, such that if I were to take the gradient of this scalar function, right, without the minus sign, or with the minus sign, doesn't matter, but we'll do without the minus sign, you get the original vector field. Okay. So yeah, if the vector field f can be written as the gradient of some potential function, some scalar function. Okay. So yeah, and again, when they, in your physics courses, when they define conservative, they might do it a little bit differently, but this is our definition here. And you can see not all vector fields are conservative. G, this vector field here, we already said was not conservative, right? We tried finding the potential function, and we just couldn't make it work. There's no match here between, what we presume to be the potential function. When we took the partial derivative here, it did not match the component of the vector field that it should have. So for that reason, it's just G was not conservative here, right? So yeah, some vector fields are conservative and then some aren't. Which ones are conservative? Well, if you can find a potential function, if you can find this little f here, then you know it's conservative. If you cannot find the little f, then we know it's not conservative. Okay. Okay, so we're given some generic vector field, right, with components m and n. So this is a vector field in the plane. We'll go back to the vector fields in space in just a second, right? So the question is this vector field f conservative? And again, that's not a simple question to answer, because we literally have to find our little f, our potential function, right? And remember how we do that. We set the two components, m and n, equal to the partial derivatives, and then we just have to do the integral, right? So we integrate m with respect to x, and we integrate n with respect to y, and we have to come up with the same function, right? It looks like we're doing two different things here, and we're getting two different answers, but this has to be the same for both, right? Up to a constant, right? Up to a constant c, these have to be equal, right? And the problem with the g in the previous example is that we could not get them to be equal no matter what we do. And if they're not equal, then then it's just not conservative, right? So yes, these have to be the same. I just want to make that clear. Well, at least up to a constant. Put that back. So they can differ by a constant, but they can't differ by a function of x or y, or certainly not both. So, okay, so that, again, that's pretty, that's pretty complicated to check. And we did two examples of that, right? One which was conservative and one which wasn't. But let's suppose I just want to know, is it conservative? I don't care about finding the little f. I don't care about finding the potential function. I just want to know, is it a conservative vector field or not? So it turns out there's an easy way to answer that. It just has to do with these partial derivatives, right? Remember when you take the second partial derivative, if I take the second partial derivative of f with respect to y and then x, or if I take the second partial derivative with respect to x then y, and again, I know this is backwards. This is, right, this is yx, and this is xy. You remember that it doesn't matter, right? That these two partial derivatives will be equal, right? So it doesn't matter what order you do the second partial derivatives in. X first and then y, and then, or y first and then x. You get the same thing every time. Okay, not every time, right? There's certain functions where this does not apply, but we're never going to see those, right? Those are essentially functions that are not differentiable enough. And, right, so our functions will be nice continuous differentiable functions, where this will always be true. Right, so if I take the second derivative of f, right, with respect to x, well, let's do it one step at a time, right? So I'm going to take the partial of m with respect to y, because that's the partial with respect to y of the partial of f with respect to x, right? In other words, it's the second partial derivative of f, first with respect to x, then y. Right? So it's fxy. But if I take the partial of n with respect to x, I get now the partial with respect to x of the y partial of f, right? In other words, we do the y first and then the x. So this is fyx. But of course, these are equal, right? If these are equal over here on the right, these have to be equal on the left. So we get this nice condition here. We can say that f, which is mi plus nj, again, these are functions of x and y in general. This is conservative if I take the partial of n with respect to x, and I get the same thing as the partial of m with respect to y. So this is a nice way to test whether a vector field is conservative. Okay? It does not give you the potential function. The only way to find the potential function is to do these integrals over here on the right, right? The way we did it earlier. Okay? So, yeah, let's just check. In fact, let's do the same examples we had earlier, right? The first example, if I remember right, the vector field f had components 2xy cubed and 3x squared y squared, right? So that's your m and n, respectively. So is this vector field conservative? Well, we know it is because, well, we already found the potential function, right, plus c. But, you know, we did that the hard way, right? So here's the easy way. If I take the partial of n with respect to x, so that's just 3x squared y squared. If I take the derivative of that with respect to x, I get 6xy squared, right? Now let's take the y partial of m, right? So with respect to y, take the first one, that's the m, 2xy cubed. And now take the derivative with respect to y, I get 2 times 3 is 6 times x times y squared. Well, look at that. These are equal. So, of course, this tells us alone that the vector field f is conservative, which we already knew, but now we know for sure now, right? Right. However, again, I want to express that this has nothing to do with the potential function, right? When you take these partial derivatives, they have to be equal to be conservative, but this is not the potential function, right? This is not little f, right? Not even close, right? Here's little f. It's x squared y cubed. There's nothing to do with the 6xy squared. So whatever function this is, you're just checking to see that they're equal. And if they are, it's conservative. And if they're not, it's not conservative, right? So let's look at the other example that we had, right? That was capital G, which was just, x squared xy. So that's your m and n, right? M comes before n, right? So if I take the partial of n with respect to x, that's the partial of x times y. With respect to x, remember y is a constant, you just get y. And now if I take the y partial of m, remember m was x squared, and the derivative with respect to y, well, is 0, right? It doesn't depend on y. So, right, we get two different answers. Y does not equal 0. Well, look, I mean, you can say y is 0 if you're only along the x-axis here. But look, we're looking at the whole vector field everywhere, not just along the x-axis, right? We're looking at vector fields everywhere in space. Not that, right, this is not a good representation. I'm just drawing a generic vector field here. It's not the graph of this, I promise you that. So yes, of course y is 0 along the x-axis, but these two functions have to be equal everywhere, for all x and for all y, right? And these are simply not equal, right? Not in general, not always. So for that reason, this G is not conservative, right? Which is nice to know, because now there's no reason to check. There's no reason to find little g, because there is no little g, right? There is no potential function. So we can look at what we did earlier. We tried to find that g of xy, and it just didn't work. There is none. So that was a waste of time, because all we had to do was check this, which is a little bit easier, and then we can conclude that there is no potential function g. However, if it turns out they are conservative, right, if these two things are equal up here, that does not tell you the potential function. Then you have to still work through all these integrals here, these two integrals, in order to find the potential function. Okay? All right, and finally, what happens if the vector field is in space? So before we can discuss whether a vector field in space is conservative, again, we know that the definition is, can we find a potential function? But here, we're given a vector field in space. And before we can talk about whether it's conservative or not, we need to define a specific vector field here. So we have a vector field, right, m, n, and p. And this might be the last time I write this out. We know that m is a function of x, y, and z, as is n, as is p. So just to abbreviate this, I'm going to write the vector field, which we know is a function of x, y, and z, right? I mean, it doesn't have to be. It could be just a constant vector field. Every point in space gives you the same vector here, right? So that's a boring vector field, right? It might be, 3i plus 2j minus 5k, right? So this is a vector field that does not depend on x, y, and z. It's the same everywhere. Okay, so that's a constant vector field. But that's a very special case, right? Very special case. Okay, so here's the definition, right? We're going to define something called the curl of the vector field f. And we can write that as, just write it out, curl of f. But it turns out it's going to be related to this del symbol, this nabla symbol. It's del cross f. It's the cross product of del and f. Okay, so what does that mean, right? Remember, del is not a vector, but it's a vector operator. Right? So remember, we used the same del when we talked about the gradients. Right? This symbol is really just a sort of a vector operator. The three components are just the partial derivatives. Right? Right. Just the partial derivative symbols, right? Obviously, if you're taking the gradient of a function like little f, then you're taking the partial derivatives of f. yeah, F, to get the three components, right? So that's one way we can use this symbol, is to take the gradient, right? This is just the gradient we know from before. Right? So this is a little different, right? This is the curl. So we need the determinant, right, for the cross product. The first row will just be the three unit vectors, I, j, and k, right? The middle row will be, well, this vector del, right? It's just going to be the vector with these three partial derivative symbols, right? And then F is, well, this vector here with the three components, right? For now, we're just calling them M, N, and P. Okay? So this curl of F gives you a vector field, right? This is a vector field. And it might help to write them out in terms of their components. Right? So the I component will be, well, this determinant here. So it's going to be the partial of p with respect to y minus the partial of z with respect to, sorry, the partial of n with respect to z. So yeah, let's write that out. So it's going to be the partial derivative of p with respect to y minus the partial derivative of n with respect to z. And that's just the I component, right? Plus the j component. Oh, I'll put the j after this convention. We erase the middle column and we do the partial of m with respect to z minus the partial of p with respect to x, right? Because we're going, right, we don't want the negative sign here, so let's do it backwards. Partial of m with respect to z minus partial of p with respect to x. That's the j component. And then this determinant here, the usual order, partial of n with respect to x minus the partial of m with respect to y, and that's the k components, right? So, yep, you get another vector field, right? This is a vector field because it has three components. And in general, these partial derivatives, well, they could, of course, just be constants, but they're more likely they're going to be functions of x, y, and z as well. Okay? So in other words, this is our new, well, I can't use m, n, and p, can I? Because it's a new m. This thing is our new m. So I'll call it m twiddle plus n twiddle j plus p twiddle k, right? Not the same n, right? Not the same p as this, not the same n as this, right? Obviously, they're going to be different here. Okay, so you get a vector field. That's the point. Right. So let's just do an example. Let's actually calculate the curl of a particular vector field. So let's suppose our vector field f would dispense with the x, y, and z. We know they're functions of x, y, and z, right? Yeah, let's suppose it's just a vector field with components 4x squared y times I plus yz times j plus, let's do xy squared z times k. Okay, so that's my m, n, and p respectively. Or, yeah, maybe just to make it clear, let's do them vertically here, right? So this is m I plus nj plus pk. Okay, and the question is just find the curl. Okay, right, because remember, we can't take the gradient of capital F, right? We can't do this, right? What does that even mean, right? It's, right, you take the gradient of a scalar function, and that gives you a, sorry, not of x, right? Of x, y, and z. That gives you a vector field. So what does it mean to take the gradient of a vector field? Yeah, that doesn't seem to make a lot of sense. I mean, you could write this out, of course, and in fact, if you take an advanced electromagnetism course, you do this. So this is something formal that you can write out. Excuse me, it turns out to be something called a dyadic or a dyad. I don't remember which. or more generally sort of a tensor, although I'm not even sure it qualifies as a tensor. In either way, we're not going to bother with this, right? So for our purposes, this just doesn't make sense to us. But it's something that you can get into a little bit later if you want. All right, so yeah, let's calculate the curl here, right? So here's the formula for it. You can either think of it in terms of the determinant or all these partial derivatives. And to be honest with you, I'm never going to remember this, right? I'm just not going to memorize this. You can if you want to, but it's on your formula sheet. And I just go back to the determinant here, right? So if I want to calculate, again, either the curl of f, or I'll just write it as del cross f, I'm just going to write down the determinant, right? I, j, and k, and then the x partial, the y partial, the z partial, and then the three components. 4x squared y, yz, and then xy squared z here. So now I can take the partial derivatives almost in my head, right? The y partial of xy squared z is going to be 2xyz minus the z partial of yz is just y. So that's the I component. And then the j component, right, the y component, if you will, is going to be the partial of this with respect to z. Well, that's just 0 because there is no z there, right? It's a constant. Minus the partial of this with respect to x. And that's going to be y squared z, right? Times j. And then for the k component, or the z component, it's the x partial of yz, which is 0 again, minus the y partial of 4x squared y, so that's just 4x squared, times k, right? So yeah, this is a vector field. Here are the three components, right? And this is the curl of f, right? So you take a vector field, you take the curl of it, and you get another vector field, right? So yeah, this is my new m and p. Again, we should put little twiddles on them because it's not the same m, n, and p that we had originally. These are very different m's, n's, and p's. They're different components, right? So when you take the curl of a vector field, you're not going to get the same vector field. Or are you? I guess that's a good question. Is there a vector field whose curl is itself? Can you get the same m, n, and p? Right. So obviously not in this example, but there might be a vector field whose curl is itself. I can think of one right off the top of my head. But the question is, are there others? So what's the sort of condition here? Yeah, the one I can think of off the top of my head, of course, is the most trivial of vector fields. Sorry, capital F. It's a lousy capital F here. Just take the vector field with the three components, 0, 0, and 0. The 0 vector, right? So the most boring vector field everywhere, it's basically that at each point you have the 0 vector. So there's no arrows, they're just points. Very boring. But when you take the partial derivatives of these, you still get 0. So obviously the 0 vector field is its own curl. So of course, if you take the curl of 0, you get 0. But very boring, right? Okay, so let's not worry about that question. Yeah, so in general, the answer is no. Obviously, it works with 0 and maybe some other vector fields, but I'm not quite sure. I haven't thought about this enough. It's a good question, something to think about, but don't spend more than a few minutes on it because it's not worth it. It's probably not something I would ask on a test. Let's put it that way. That would be a challenging question. All right, so we know how to compute the curl, right? But that doesn't answer the question, right? Given a vector field, how do we know if it's conservative, right? We know the answer for a plain vector field, a vector field with only two components, and it's just this condition up here, right? So what is it with three components? Well, if you notice, this is the x partial of n and the m partial of y, if you look at the third component here, that's exactly what we have, right? If we take the x partial of n, and that's equal to the m partial of y, then when you subtract them, you just get 0, right? So then we would know this is conservative, right? If we get 0 here. Oh, sorry, not 0 as a vector. 0 as a scalar for that component. But you get the idea. Then this would also have to be 0. This would also have to be 0. So that leads us to the following condition here, right? A vector field in space, right? So capital F, a vector field in space with these three components, m, n, and p, is going to be conservative, right? If the curl of that vector field is the 0 vector, right? So we know the 0 vector field is conservative, but that's, again, a boring one, right? And so we know this vector field up here, right, this vector field is not conservative. Right? How do I know that? Well, we took the curl, and here it is. Right? This is clearly not the 0 vector field. It's not 0, 0, 0. Right? Unless you get 0 for all three components, right? If you get 0 for all three components, it's conservative, right? Even if one component is not 0, right? So if you take the curl of the vector field and you end up with 0, -2, 0, well, that's not the 0 vector, right? That's not 0, 0, 0. So if you get this, you know that your f is not conservative. Right? If you get anything other than 0, and this clearly is not 0, then you know your vector field is not conservative, right? And then you know that there is no potential function. There is no little f here. So why bother finding it when you know it doesn't exist? Got it? Yep. So if you take the curl, if you get 0, you know it's conservative. If you get anything other than the 0 vector, and that means all three components being 0, then you know it's not conservative, right? So if you make up a random vector field, chances are pretty good that it's not going to be conservative, right? Most vector fields are not conservative, right? But the ones that are become very important, and of course we talked about them conserving energy, but we're not going to do any more of that. Okay, so let's just do an example. Here's a vector field with three components, right? M, n, and p. And the question is G conservative? And if it is, find the potential function. Find the little g, right? Right. And I was going to use f, but it's a different vector field, so we'll use g here, right? And notice I'm writing it this way. Of course, we can also write it this way: 3x squared plus y times I, right? Plus x minus 2z squared times j plus, well, negative, so maybe just minus 4yzk, right? Minus 4yz times k. Either way, right? It's a vector field. So just to make sure you know, right? M is 3x squared plus y, right? N is x minus 2z squared, and p is -4y times z. Okay. So is it conservative? Well, to answer that question, we should take the curl of G, right, which is del cross G. I was going to write F, but it's del cross G. And again, let's write out the determinant. Right, so partial with respect to x, partial with respect to y, partial with respect to z. I needed a little more space here. So m is 3x squared plus y. Y is x minus 2z squared, and z, the p component, is -4y times z. And yep, so taking the partial derivatives in the determinant, so the I component will be the part, these aren't 2's, by the way. I know I'm a little sloppy here. I know yeah, unfortunately this symbol here for the partial derivative, right, if you're not careful, it can almost look like a 2 if you're really sloppy. But those aren't 2's, obviously. Those are partial symbols. So anything that looks like a 2 here is really just the partial derivative, right? And I know this might not look familiar, right? If I write this with the subscript y, what I really mean is the partial with respect to y, right? So yeah, it's because I'm going to run out of space if I write these fractions here. So this is just shorthand notation, right? So I'll leave this one up so we know what that means. All right, with respect to y, we're going to get negative 4z minus a negative 4z, so plus 4z. That's the I component. So that's going to be 0. That's a good sign, right? And now, let's see, we get, oh boy, the partial with respect to z of this, well, that's 0, right? And then the partial with respect to x of this, and that's also 0. So we get, well, 0 minus 0 here, right? 0 minus 0, so the j component is 0. But hang on, we don't know that it's conservative yet. We have to check all three components, right? So now we have to do this partial derivative and this partial derivative. So the partial with respect to x of x minus 2y squared, that's going to be 1, right? Because the derivative of x, oops, is 1. And then minus the partial of this with respect to y, well, the derivative of y is also 1, right? And 1 minus 1 is 0. So we get 0i plus 0j plus 0k, and that is definitely equal to the 0 vector. So the curl of G is in fact 0, right? So the answer then has to be yes. If the curl is equal to 0, then G is conservative. Okay. So, yep, if the curl is 0, it is conservative. If the curl is not 0, it's not conservative. Right. And if it wasn't conservative, we'd be done. But since it is conservative, that means there is a potential function, and now we have to find that as well. So yeah, in some sense, we didn't have to do this curl, because if we just look for the potential function now, although I'm going to need my m, n, and p here, so maybe can I just copy this down? Yep. Right. So now we're going to use this to find the potential function little g as a function of x, y, and z, right? So remember what that is, right? That's going to be little g. If we take the gradient of that, I get capital G, right? So in other words, this has to be g sub x, this has to be g sub y, little g sub y, and this has to be little g sub z. And you know what I mean by that, right? I mean the partial with respect to x, right? That's y, right? So to find g itself, we're just going to integrate, right, m with respect to x. That's the integral of 3x squared plus y with respect to x. So we're going to get x cubed plus xy plus now some function, I guess I'll call it h1, of this was with respect to x. So this could be any function of y or any function of z. Right? It could be, yeah, some function of y and z. So h1 of y and z now, right? All right, now do the y partial, which was what? It was x minus 2z squared. Right? So to get your potential function, we're going to integrate n, but with respect to y now. So x minus 2z squared with respect to y is going to be x times y minus 2yz squared. And then plus any function that doesn't depend on y. So that could be a function of x or a function of z, or both, right? And finally, the z partial derivative of y. Again, it's could look like a 2, or could look like a backwards 6 too, if you're not careful. So that was negative 4yz. Okay, so that should be a quick integral here. You're just integrating p with respect to z. So the integral of negative 4yz with respect to z is is negative 2yz squared, right, plus any function of either x or y, but not z, because that was the integral of, that was the variable with which we took the integral, right? That's the z. Okay, so we just have to look at all these separately here and see, can we get a consistent potential function? Can we find a potential function that's the same for all three of these? Okay, so here's how I do it, right? What's the same for all three? Well, I don't think there is anything that's the same for all three here, right? No. Yeah, clearly not, right? So what's the same between the first two functions is this x and y. Okay, so that's a function of x and y. Well, this h3 can only be a function of x and y. So it looks to me like we can just use h of 3, as a function of x and y. That might as well be x times y, right? So we're gonna make this, right, equal to plus x times y in just a minute, right? All right, what else? What else do we have? In the bottom two here, we have this negative 2yz squared. So that's a function of y and z. And that might be the perfect candidate for h1, because h1 can only depend on y and z, but not x. So luckily there is no, that's h1, right? There is no x in negative 2yz squared, so that would be my h1. Okay, so now the only thing left here is this h2. This can be any function of x or z. Okay, and if you notice, this is your x3 up here. So that is probably going to be my function of x and z. It doesn't depend on z, but it doesn't have to. As long as it doesn't depend on y, then we're all set, right? So I think my h2 of x and z will have to be x cubed, right? And I think that does it. Yeah. Well, maybe I'm missing something here, right? Because notice that this does not have the x cubed either. So I think my h3 also has to contain the x cubed as well, right? That has to be there as well. Otherwise, it's not going to be there, right? And the h of x and z will be just the x cubed. So that will go here. So I think that does it. Now we can put it all together. Right? So if we just take any one of these, let's take the first one here, right? This is going to be equal to x cubed plus xy plus h1, which is negative 2yz squared. So, right, negative 2yz squared, right? But what am I missing, right? I'm missing that any of these can be, you can always add a constant, c. Okay, so there you go. That's your potential function. If you don't believe me, just do it with the second row here, the second version here. This is going to be xy, right, minus 2yz squared plus h2. So h2 was x cubed plus c. And you get the same thing, just not in the same order, but order doesn't matter. You can always change the order. And now it looks exactly like this, right? And if that's still not good enough, you can take the third row and use that as your potential function. Right? The point is, it shouldn't matter. You should get the same thing for all three, right? All right, now what is h3 of x and y? It's going to be all of this, right? It's going to be xy plus x cubed plus c. And again, except for the order, this is all the same thing. So I'll put the x cubed first, then the xy, and then the minus 2yz. Oh, sorry, not cubed, squared, right? Squared. plus c. Okay, yep, same thing for all three, right? So that's your potential function, right? And there has to be one because we already showed that g is conservative by taking the curl and showing that it equals 0. So if the curl is 0, and again, make sure you check that right and make sure it's correct, then there's guaranteed to be a potential function. Now finding it, again, is this process of finding all three integrals here and then just mixing and matching. Right? I mean, there's other ways of doing it. If you can do this some other way by, just doing one and then finding the h's for the other two, that's fine too. I like to do it this way, mixing and matching, because everything should match here. And, if g was not conservative, then there's no reason to do this. However, let's say we didn't even bother finding the curl. Let's just say we assumed that g was conservative, right? And we didn't bother doing any of this. Well, you could still do this, right? But what'll happen is that you'll get something that won't match up. Remember, that happened in one of our examples earlier, the g function, the g vector field, which was just, I believe, x squared I plus xyj, right? And there's no curl here because there's no k components. Although, I suppose you can find the curl of this now, assume that p is 0, and most of your things will be 0 here. But when you have a vector field in a plane and there's only two components, then you only need to check this condition here, right? But when you do have a vector field in space, you have to check essentially all three conditions, right? That all three components have to be 0, right? And again, I think this was what? This was partial of p with respect to y minus, or equals the partial of n with respect to z? Yeah, I think that's it. Yeah, because this is p, this is n. Okay, fair enough, right? So yeah, you get this equation, you have to check that, and you also have to check that partial of m with respect to z is equal to partial of p with respect to x. And then here you have to check that the partial of n with respect to x is equal to partial of m with respect to y. And that's, again, this final condition here. That's the only one you need for a vector field in a plane. But for a vector field in space, you have to check all three of these. Or just take the curl and check that it's 0. It's the same thing. Okay, so I hope you're getting the hang of determining whether a vector field is conservative, and if it is, find the potential, and if it's not, then you're done. There's no reason to look for the potential. There's no reason to do any of these integrals here, because there won't be a consistent g for all three of these, right? Okay, I know this is a long video, but there's one other concept that's kind of important here. Given a vector field in space or in a plane, we want to calculate what's called the divergence of the vector field f. And the divergence, right, you can abbreviate div for divergence, but it's actually just the dot product of del and f, right? So remember what del is. It's the vector, sort of a vector, with the three components being the partial derivative symbols. Right, these things here. And f, well, f is this vector here. It has three components, m, n, and p. Okay, so remember what the dot product is. It's a lot easier than the cross product, right? All you need to do is multiply this times this. Well, okay, you're not multiplying here. You're taking the partial of m with respect to x, right? Plus, right, this is not a vector, right? Dot product is a scalar. The y partial of n, so the partial of n with respect to y, and then plus the z partial of p. So take the partial of p with respect to z. And there you go. This is called the divergence of a vector field, right? And be very, very careful here. This is not a vector, right? Remember, the dot product is a scalar. The cross product is a vector. So the curl was a vector field. This is not a vector field. This is not a vector field. So please, please, please do not put an I, j, and k here. That's not what this is, right? It's not a vector field. It is a scalar field, right? It is a scalar field, right? Right. So it could. Right. So it's some function of x, y, and z. But I'm not going to write, because if I write it this way, you might just assume that that's the potential function, and it's not. Right. So yeah, the divergence has nothing to do with the potential function. Okay. Yeah. Let's take a look. Let's do an example. It's not example 1. It's just an example. So here's a vector field. F is a function of x, y, and z. So let's say the three components are 2x to the 4th times z. That's the I component, plus, let's do sine of yz is the j component. And then, again, I'm trying to keep it interesting here. How about y times e to the xz for the k components? Okay. So yeah, again, this is just mi plus nj plus pk. So yeah, the question is to find the divergence. So let's calculate the divergence of f. Right. Of course, you could take the curl as well. But maybe we'll do that later. But let's take the divergence, because it's much easier, right? So, yep, this is just the partial of m with respect to x, plus the partial of n with respect to y, plus the partial of p with respect to z. No I, right? No I, j, or k here, right? All right, so this is our m. If we take the derivative of this with respect to x, we get 8 times x cubed times z, z being a constant, right? Plus, and then the derivative of this with respect to y will be z times the cosine of yz, right? Plus, and then the derivative of this with respect to z will be xy times e to the xz. And there you go, right? This is a function of x, y, and z. But again, to warn you, this is not the potential function. This is not the potential function. It's not the little f. I just don't know what other letter I can use here. Right? I can use little g, but again, that we can also use that for a potential function. So, right. I mean, we don't have to give it a name, right? We just call it the divergence of f, right? And it's a function of x, y, and z, but it's not a vector function. It's a scalar function, because the dot product is a scalar, right? Yeah, so each point in space will give you a different value, a number, but not a vector, right? So think of like temperature, right? Could be a temperature function or something. Right. After all, we don't even know that there is a potential function. This might not be conservative. And if it's not conservative, then there is no potential function, which means the divergence has nothing to do with the potential function, right? And even if it is conservative and there is a potential function, I promise you it's not this. This will not be the potential function. I mean, I guess you can ask the question, well, is it ever can it be the potential function for some vector field, right? And again, I don't know the answer to that. I haven't thought enough about that. It's a good question, right? In other words, can the divergence of a vector field actually end up being the potential function if the vector field is conservative? And yeah, I'd have to think about that for a while. It's a good question, but I mean, my guess is no. My guess is that there just aren't any, but there could be. Obviously, we could say the zero vector field, the divergence is 0, and then the curl is also 0, so it's conservative. But then the potential function is, well, just a constant. So Right. But remember, the divergence was 0. So then you're right, the constant might not be 0. So even in that case, the answer is no. So no, my guess is that the answer is no here, right? After all, there is no plus c here. So be careful you don't put a plus c there. Right. Okay, so yeah, divergence has nothing to do with the potential function in general. Right. Now, can we take the curl? Well, sure we can. Maybe we won't do it with this, right? Let's do one more example where we take the curl. Okay, yeah, I know this is a long video, but I want to do 3 more examples here. So here's a vector field, just some generic vector field, and we want to find the divergence, the curl, and then this interesting thing, we can take the divergence of the curl, right? Because the curl is a vector field, we can take the divergence of a vector field. So we're going to do all 3 of these. So maybe let's just start with the divergence, because that's the easiest one. At least once you get used to it, it's the easiest one, right? So it's just the partial with respect to x of m, which is xy squared, plus the y partial of yz cubed, plus the z partial of x y to the 4th z squared. And just doing each of these separately, you get y squared plus z cubed plus 2x y to the 4th times z. And that's it, right? No ij's and k's here. This is not a vector field. It's a scalar field. Okay. Yeah, now let's do probably the hard one is the curl of f. So I'm going to set this up the usual way by using the determinant, ij and k, and then the x partial, the y partial, and the z partial, and then the 3 component functions, xy squared, yz cubed, and xy to the 4th z squared. Oops, that should be straight for the determinant. Okay, do I have enough space here to squeeze this in? Let's see. So the y partial of, I probably don't. I'll go down here now, right? So, right, remember we're doing this determinant times I. So, and I know I've been doing this awfully fast, but you know, if I write this out step by step here, this could take forever. So we're doing the y partial, I guess I'll do it, right? In case I lost some of you in the previous problems. Right, so this is the y partial of xy to the 4th z squared minus the z partial of yz cubed. And that's just the I components. To get the the j component, we do this determinant. So the partial with respect to z, I should use brackets here, right? Of xy squared, well, we know that's 0, right? Minus the x partial of xy to the 4th z squared times j plus, and then this determinant here, so the x partial of yz cubed minus the y partial of xy squared. And that's the k component, right? All right, so now just calculating these partial derivatives, what are we going to get? We're going to get 4x y cubed z squared minus 3yz squared times I plus, the partial with respect to z of xy squared is 0 minus, now the x partial of xy to the 4th z squared is just the y to the 4th times z squared. It's the j component. And then the k component will just be 0 minus 2xy. Right. So yeah, it's kind of a long vector here, but this is the curl. I'm going to make sure I get it right. I hope it's right. xy. Great. so that's the curl. Either way, you can leave it in terms of I, j, and k. I like to write it out as with the bracket here. Right? And the last thing we're going to do here is take the divergence of the curl. So this is now the curl, right? This is my new m, n, and p, right? Not the same, obviously, as this m, n, and p up here, right? But I just don't want to use different letters. And I don't want to use prime because that looks like derivatives. That's why I use these little twiddles here. Okay, so our the final thing we want to do here is take the divergence of the curl of f. So take the divergence of the curl of f. Right, now we already took the curl, so we're not going to do it again. It's this vector up here, right? So we just need to take the divergence. Remember what the divergence is. It's just the partial of m twiddle with respect to x plus the partial of n twiddle with respect to y plus the partial of p twiddle with respect to z. So the partial of this with respect to x, oops, that's y cubed, right? Z squared minus 3yz squared, okay, plus the y partial of n twiddle, which is just negative y to the fourth z squared, and then plus the z partial of p twiddle, which is negative 2xy. Okay, so what do we get here? I think if we take the partial with respect to x, we're just going to get 4y cubed z squared, minus 0 here, right? Because there's no x in that term. So that's just a 0. Can't draw a 0 here. There we go. All right, plus, and now take the y partial of this. We're going to get negative 4y cubed, right, z squared. And then this doesn't depend on z, so that partial derivative is 0. Okay, so what do we get? We get 4y cubed z squared minus 4y cubed z squared. Look at that. That's just 0. Right? They just cancel out. So if you take the curl of a vector field and then you take the divergence, it looks like you get 0. Now maybe that's a coincidence, right? That only happened for this example here. It turns out it's not a coincidence, right? So this is true for any vector field. In fact, this is a theorem. We can prove it. It's proved in the book. If f is any vector field, okay, maybe not any vector field, but any C2 vector field. What do I mean by C2 vector field? It's m, n, and p has continuous second partial derivatives. So continuous second partial derivatives, right? And if you've noticed, all our examples are not just continuous, but differentiable. The second derivatives are continuous. The third derivatives are continuous. We're only dealing with nice continuous functions, right? And, you know, infinitely differentiable. Differentiable 2 times, 3 times, 4 times. So as a practical matter, this is almost always going to be true. And if it's not true, then, you know, it's a rather pedantic example, and we're probably not going to go through that, right? But if right. So for our purposes, if f is any nice vector field, I'll just call this a nice vector field, then the divergence of the curl will always be 0. Right? But be careful, not 0 as a vector. Remember, this is the divergence. The divergence is a number, not a vector. Okay? So you can also write it this way if it helps. The divergence of the curl of any vector field, of any nice vector field, right, is just 0 as a scalar. Okay, so I'm not going to prove it. The proof is in the book, and you basically just work it out, right? Just do this for any vector field. Just give it components m, n, and p. Vector, right? And effectively, you're taking the derivative of a derivative, right? You're getting second derivatives, which is why we need this condition that that second derivatives have to be continuous. Right? What's going to happen as a practical matter when you work this out, right? You're going to get the second derivative of, say, p with respect to, say, x and y minus the second partial of p with respect to y and x. But remember, these are equal, and that's what gives you 0 in these cases. So when you work it out, I'm guessing you get all these mixed partial derivatives. When you change the order, you get them to be equal, and when you subtract them, you get 0. So that's not the proof, but that's the idea of the proof here. So I think this video went on long enough. I know there's a lot of material here to get through. Just do the best you can with the homework. You know, do some examples of calculating the divergence, calculating the curl, and in particular finding vector fields, conservative or not conservative, and finding potential functions only when they are conservative. So yeah, a lot to get through. So maybe I'll just give you a quick summary here, right? So we talked about vector fields, obviously, it's the main topic here. Make sure you know what it means to be a conservative vector field. Conservative vector field, in particular, it just means that there is a potential function whose gradient is that vector field. So f is the potential function. Potential function, right? And make sure you know how to determine if it's conservative by using the curl. If the curl of the vector field is the 0 vector, then you know, the vector field capital F is conservative. And then you should be able to find the potential function, right? And make sure you know how to find the divergence of a vector field. Again, it's just this. This is all on your formula sheet, so you don't have to memorize any of these. You know, when you get deep enough into your physics classes and your, engineering classes, you're going to encounter these things so often that eventually they will become second nature, finding the divergence and the curl. Certainly if you go on to more math courses, advanced calculus and differential geometry and courses like that, you're going to see these all the time and in different contexts as well. So let me see, am I forgetting anything? Vector fields, conservative, curl, and divergence. I think that's it for now, right? Yep, and just make sure you know the combinations that you can do, right? If you have a vector field, right, you can take the curl of that vector field, and you can take the divergence of that vector field. You cannot take the gradient of that vector field. I mean, you can, but we don't know what that is, and we're not going to worry about that, right? We're not going to worry about taking the gradient of a vector field. It's an unusual object. It's more complicated than we need it to be here. So if you have, let's say, a scalar function, what can you do with that? Well, you can take the gradient of it, but that's it, right? You cannot take the divergence of a scalar function. That doesn't make any sense. You cannot take the curl of a scalar function. That also does not make any sense, right? Whether you have x, y, or x, y, and z doesn't matter, right? So that does not work, right? But as we just saw, you can take the divergence of the curl. And if you do that, you basically just get 0, always. But remember, the gradient is a vector field. And it turns out you can take the, you can take the divergence of the gradient, right? And in fact, what you get is something called the Laplacian, right? And this has to do with, again, thinking about this as like a second derivative. You get Laplace's equation if you set this equal to 0, or Poisson's equation if it's some function. And this has to do with, if this does equal 0, you get harmonic functions. But we're not going to worry about that. You can also take the curl of the gradient of a scalar function. And as it turns out, that has to be the 0 vector, right? It's a vector field, but all 3 components are 0. Okay, so that's also, you can actually prove that. Again, that's also looking at the second derivatives and seeing that the mixed partials are equal. I think that's what happens if you work that out, right? So because of that, the curl of the gradient is also 0, right? And in fact, you could actually take the curl of the curl of a vector field, and that gets to be a little too complicated for us. So this does come up in advanced electromagnetism courses, possibly, you know, your electrical engineering courses will have to deal with that in terms of magnetic and electric fields. But luckily, we're not going to encounter this in this course. All right, that's it. That was a long video. It's a long section because there's a lot to deal with here, but it's important that you go through this carefully because in subsequent sections, we're going to deal with this stuff all the time. So you got to get used to it pretty quickly. Okay, best of luck.